Hi, I'm Stefan. Welcome to the TwoStack Developer channel. In the previous episode, we looked at a novel way that Alice was able to add constraints that restricted the way in which Bob could create his spending transaction. Today, we're going to look at a technique that extends what Alice was able to do with the constraints that she was able to place on Bob's transaction, and extends this to do something that was thought, or that was previously thought, to be impossible within Bitcoin. And that is to maintain state between transactions. Essentially what we'll be doing is Alice will now use the fact that she has access to Bob's pre-image to define a state transition function within her output script, and in that manner essentially constrain the way in which Bob can create his transaction to include this very specific way in which Alice would like from this point forwards for all state transitions to data that she has inside her output to be manipulated for all subsequent spending transactions. If that was a mouthful, let me explain. Let's get started. A quick aside, both the previous episode as well as this one, you may or may not have noticed, but I think I want to mention this. Both of these two episodes are actually based on blogs or Medium articles that were written by the creator of sCrypt, Xiaohui Liu. Those links will be in the description down below. I think it is a brilliant resource for you to go and look at those blogs and read the content there, because essentially both the previous episode as well as this one really are just my interpretation and my explanation of what I've read there. Yeah? Okay, let's get going. The first thing that we need to do is to actually get or figure out a way for us to have data inside our smart contract, and then how to actually access the data within the smart contract. Let me quickly explain this technique by drawing first the input that Bob will be. So this is going to be Bob's input, right? And Bob will be providing us with a pre-image in his input. And the next part is that this is going to be our smart contract, right? So Alice composes the smart contract over here, which is actually also the output, the UTXO that Alice is composing. Now, ideally, right? Let's say that we want the data to be appended to the end of Alice's output. If we are able to determine the size of this input script, or rather of the output script here, I'm going to call this size D. If we can determine the size of D, and if we know if we basically state that we have a fixed size data structure over here, right? Then we can basically take the size of this fixed size data structure, which I'm going to call X. Then if we want to know where to start reading our data, all we need to do is to take the total size D of Alice's output script minus the size X of her let me write this in this way. Then we can have the offset where we want to start reading will actually be D minus X. So convince yourself that this is actually correct, right? That the distance D, or rather the size of Alice's output D, minus the size of the fixed size data structure that we define will actually give us the offset here that we want to start reading at in order to read out our data to be able to manipulate. Okay, so where do we get the size that we want here, right? So we want the size of the output script D here. If you recall, the pre-image actually has this structure, right? And right here in the pre-image, we have an output script. The output script that is actually provided by Bob in the pre-image, this output script is the same as this output script here. So when Bob constructs his spending transaction and he provides the input in the pre-image of the spending transaction, part of that pre-image that he's providing is actually the output script here. Yeah. So if we can now, inside our smart contract that we're composing in the output script, yes, if we can write into code there that we want to grab the output script, yeah. So if, and I know basically that there's a utility function, right, where we can get the pre-image output script. I don't actually know if these variable names are correct, but we can get the output script like this. And if we then take the length of the output script, this will give us this number D, or the variable D that we were talking about. Now we already know what we want the size of the data to be, right? So that basically gives us the ability now to, because we basically determine what the size of the data D here is going to be, like this is going to be X. Then we can now calculate D minus X to determine the offset where we want to read the data from. Let's go over to a smart contract and actually code this up so that this becomes a bit clearer for us. Yeah. Okay, so we left off here, right, in our previous episode with this contract called pushtx, and the pushtx contract, if you recall, was just us demonstrating that we could place this requirement over Bob to provide his pre-image, and that and then we added this additional requirement on the nlock time, where we restricted Bob to essentially needing to provide in his transaction an nlock time for his transaction that matches this requirement here. I'm going to remove that part from what Bob did and move straight into how we can actually get the length of the script where we basically need the length of the script, right? So if we're working under the assumption that we have data at the end of our script, so this is going to be our assumption. We have data at the end of our output script. This is going to be our assumption that we're working under, which means that we need to get the length of the script and then basically grab the data at the end. The second assumption is going to be that data has a size of 1 byte, right? So this is going to be an arbitrary restriction that I'm basically going to determine as the creator of the this constraint, that, well, my data is going to be a size of 1 byte, and I'm going to call this data a counter. I just want this to be a counter. I will now talk about, okay, I'll talk about what that counter actually means and how we actually use it in a second. Let's quickly look at how we can actually get the, let me get the length of the output script. So I'm going to call this the pre-image output script. There's a utility function called script code. Script code generally in Bitcoin refers to the code minus the stuff that basically gets stripped off as a consequence of opcode separator, but we won't talk about opcode separator now. Let's just, for the purposes of this discussion, say that script code, when we pull out script code from the pre-image, we're actually referring to the output script. Script code is just sort of an internal name that the Bitcoin code base uses. The node, the C++ code base uses this word, script code. It's again leaky abstraction. This is just the output script, right? Okay. Anyway, so util script code for that gives me the actual output script, and if I then want to get the length of that, I can say the script length is just the length of this array in bytes, right? So this pre-image pre-image output script. The length of this pre-image output script is my length in bytes. Now, how do I restrict Bob to only allow him to increment my counter by 1? I want to constrict him to only allow him to increment my counter by 1. How do I do this? Well, it's going to take sort of a 3-step process. I can say that step 1, I'm going to increment the counter. Like, I'm going to grab the data. Okay, grab the data in the counter. Right, that's going to be my first step. Grab the data. And then next step, I can say increment the counter myself. And then in the third step, I can say, okay, now that I've incremented the counter, reconstruct the output script. And then I need to figure out like, how on earth can I now do this? Okay, well, I could say that I can then require that the hash of this output script that I've created has to be equal to the hash of the output. So this hash of Ellis, let me write it like this, of Ellis's output script has to equal the hash of Bob's output script that he has created in his spending transaction, right? If I do this, then I can kind of force Bob, but we'll get to this in a minute. I'm kind of running ahead of what I'm doing. So let me grab the counter out of the pre-image first. So I'm going to say pre-image output, output script. Now, here I'm going to have to talk about something which I did not see in the documentation, but which I saw inside the boilerplate code. That's the array slice operator. This is very similar to the way that Python uses the colon for slicing arrays. You can essentially take everything from the start of an array or everything from the end of an array, right? So if I have an array, if I have an array that's, let's say, 1, 2, 3, 4, then if I take the slice for everything from except the first element, so everything from the start, from element number 1 to the end, this would basically be equivalent to 2, 3, 4. And if I take everything except the last element, so everything from the start up and until the last element, then I would get 1, 2, 3 like this. So that's kind of the way that the array slice operator works, right? Which also means, for example, if I want the last element, then I can just say 1, 2, 3. I want everything from 3 to the end, then I will basically have 0, 1, 2, 3. Then I will basically get 4, right? There are 4 elements and I'm basically 0 indexed. If I start at 3, then I get the last one, which is 4, right? Just convince yourself that this is the way that the array slice operator works. If you're not convinced, go and read the Python documentation on it. Somebody from sCrypt who's watching this, please update your documentation. If I was just not reading the docs properly and didn't see the this operator documented, my apologies. But the section on arrays in your documentation does not cover the slice operator. Okay. I want the pre-image output script and I want the very last element in there, right? So I basically say the script length minus 1. I know the size of my element, the byte, it's 1 byte. So 1 byte from the end, right? I want to start reading 1 byte from the end and everything up until the end, which gives me that 1 byte. And that is going to be my counter value, right? This is the value of the counter. There's one problem though, which is that this returns a byte and I need an integer. There is a handy inbuilt function called unpack, which converts this from a byte to an integer. So now I've got in the correct built-in type, which is int, I've got my counter val in there. Next, I want to increment the counter myself. This is, well, fairly trivial, right? So I can say, okay, I'm not going to write that. This is going to be sort of trivial. I'm going to say reconstruct the output script and increment the counter. I'm going to do that in sort of one go, right? how do I reconstruct the output script? Well, I can now just basically take the pre-image output script, right? I already know that the pre-image contains the output script. So I've got my output script. I can now just say that the output script from the pre-image, take everything in there except for the last element, right? So this will start reading at the beginning right up and until the last element, which it won't now read. Yeah. Actually, hang on. This needs to be everything from, so I basically need the length of the script minus the size of the element that I'm, oh, come on, minus the size of the element that I'm reading, which is 1, which means that I will read everything from the start up until the n-1, or the script length minus 1th element, right? This will basically give me the output script that I'm interested in. Then I want to add the counter value incremented by 1. So I want to increment the counter value by 1, like this, right? There's only one problem. I can't basically concatenate a this is a byte array. I can't concatenate an integer to a byte array, but there's a handy function to our rescue. Again, it's called num2bin. Num2bin takes two parameters. One is the actual value that we would like to convert into a byte array, and the second one is the size of the data that we want to convert. And this is spelled wrong. And I can now assign, this is just an array of bytes, right? So I can now say that my new output script is basically everything in the pre-image except the last value plus the last value incremented by 1. So I've done both of these two steps in one go now, right? And now the last one is that I'm going to add in a requirement here, which is that, okay, before I add the requirement, I'm going to talk about about a confusing thing here, which is if I want to take the double SHA-256 of my new, hang on. I've left the step out here. I've forgotten about this, the new UTXO that I need to create. Okay, so let me not talk about this first. Come on. Oh, this IDE does not understand how to, okay, I don't understand. I don't yet know the shortcut command for uncommenting lines quickly. Anyway, I need to create my new UTXO, right? So my new UTXO is going to be a byte array. And the reason I need to create this new UTXO is because when I take the hash here, I actually don't want the hash of the output script. I want the hash of the UTXO. Need to match the hash of the UTXO. And I'll explain in a second why that is. So I'm going to say my new UTXO there is again a handy function in here. Remember that the UTXO is basically an output script plus a Satoshi value, right? That creates the Satoshis. That gives you your output script, or your UTXO rather. So my UTXO, which consists of my new output script, which has got the incremented value plus the amount of Satoshis, that is the UTXO that I'm going to hash here and require that the hash of that UTXO must match the hash of the UTXO that is in the pre-image. So within the pre-image, there is also a UTXO hash, which I can extract, which is this. So I can now just say that, well, Bob, when you create your transaction, right, you're going to have to provide a hash for the UTXO that you are creating in your pre-image. When you construct that hash, your hash should better look like my double SHA-256 hash of the UTXO that I've created here, which has got this incremented value, right? Satoshis, I'm going to, okay, let's talk about Satoshis and then we can talk about this thing again. Imagine for now, I'm going to put this as 10,000 Satoshis just to satisfy the requirement, but I want to talk about this bit over here. Hash 256, there's another built-in function called SHA-256 inside the standard library. They are very different. This one is the single SHA-256 of whatever you pass into it. Hash 256, sorry, 256 is the double SHA-256. These two functions are confusingly named. sCrypt developers, could you maybe disambiguate these two functions a little bit, please? Maybe call the one double SHA-256 and the other one just SHA-256, or SHA-256 twice versus, yeah. Anyway, so hash 256 takes the double SHA-256 of whatever you of the byte array that you pass into it, which of course is what has been done with the UTXO byte array in Bob's output as well. It's double SHA-256, right? This Satoshi value here, when I hard code it as 10,000, I'm essentially saying, Bob, you can only create a transaction output that has the counter value incremented by 1 and is exactly 10,000 Satoshis. But I'm going to be nice to Bob. I'm going to say, Bob, you can actually pass into me as part of your input script. You can tell me how many Satoshis you are locking up in the UTXO that you're creating in Bob's transaction. So Bob can now tell me, okay, the amount of Satoshis he's locking up after he has incremented the value himself will now basically, you know, he can specify at least that amount. I'm not going to restrict him on that. And that is essentially how we do that. We have now added a requirement into our smart contract that the last byte of the smart contract must contain a value that we can increment by 1, or rather must contain a value, a data value, and that anybody who subsequently provides us with a transaction, that transaction, or rather anybody who subsequently spends from this output, the transaction output that they lock funds in the spending transaction, in other words, Bob's transaction, must increment the value by 1, right? Our data value by 1. So it's kind of important to remember, or to note rather, that the way in which state is managed by the sCrypt IDE is or rather the sCrypt IDE manages state in a very particular way. And the way in which it does this is to implicitly or by convention append or assume that the author of the smart contract will be appending all data or state which they would like to carry along with the transaction at the end of the smart contract, meaning that the end of the smart contract is always assumed to have as the last code op return followed by whatever data or state it is that the author of the smart contract would like to carry along with the smart contract. It is always op return followed by something. This is very different from the way in which you might have heard of op return being used in the past, which is that you would start the smart contract with, or not the smart contract, but you would start the output script with op false followed by op return followed by the data that you would actually like to encode inside the output. There is also the second way of carrying data in a transaction, which means that you start the transaction with the data followed immediately by, or the transaction, sorry, you start the script with the chunk of data followed by an op drop, which drops the data, and then the actual script. This is another way of actually doing this. sCrypt is basically doing a third way, which is all the code associated with whatever state you would like to carry, followed by the actual data or the state at the end of the code inside your output script. It would be up to you to decide, you the developer I mean, to decide which of these methods make more sense for your particular use case. For now, we'll focus on the fact that sCrypt and smart contracts that we write with sCrypt always append the data with an op return followed by the actual data, and that we would actually access that state or that data using the method that I just demonstrated within this episode. There remains one thing for us to do, and that is to actually write code that accesses or manipulates the data or make the transaction. The one thing which the smart contract that we have written does not by itself do, and this is sort of an external step that needs to happen. It does not encode this op return followed by the data. The op return and the data, or the op return and the state, which is meant to go at the end of the script, of the smart contract rather, that needs to be done outside of the smart contract by Alice when she creates the first transaction, or rather the genesis or the initial transaction that deploys the smart contract, or eventually by Bob. It has to be created off-chain. There is no way within the smart contract to construct, even for the initial part, the data that needs to be attached to the end of it. There is also no way to, for example, you might have thought, well, you know, I could make a local variable inside the smart contract, and maybe, no. The data that is appended at the end, you have to programmatically do it. Either the IDE will do it for you. If you look inside the IDE at deployment time, right? You will notice here that there is this optional state. So I've just basically tried to do I've gone the first step in deploying this push TX, right? So it asks me to, for the initial amount of Satoshis, I want to lock in the output. Then it asks me for the state. And the state that it's asking me for here is essentially, you know, give me some hexadecimal or some hexadecimally encoded something in here, right? It's expecting that to be given to it during deployment. When I say it, I mean the IDE, the sCrypt IDE is expecting us to provide that, which means that it will then take the smart contract that we have built, it will compile that smart contract into code, into Bitcoin script, and then it will append an op return followed by the state that we have specified in there. This process that the IDE takes of constructing the transaction and then appending the data or the state at the end of the contract, we've talked about this before. And there are programmatic ways of doing this as well, right? The IDE does not, or the sCrypt IDE does not have to be the one that deploys the contract. We can deploy the contract ourselves initially using code. In any event, when we manipulate the contract subsequently, when we create subsequent transactions, that will need to be done in code as well. In the next episode, we will basically be looking at these programmatic techniques for manipulating the transaction. But that would be it for today. I hope you enjoyed the episode and that it wasn't too drawn out or long-winded, and that you were able to at least make sense of what I was saying. I will see you next time. Bye.